Hey everyone, and welcome back to the Towards Data Science podcast. Now, on the face of it, there's no obvious limit to the reinforcement learning paradigm of putting an agent in an environment and rewarding it for taking good actions until it masters a task. And by last year, RL had achieved some amazing things, including mastering Go, various Atari games, StarCraft 2, and so on. But the holy grail of AI isn't to master specific games, but to generalize, to make agents that can perform well on new games that they haven't been trained on before. So fast forward to July of this year, and a team at DeepMind published a paper called Open-Ended Learning Leads to Generally Capable Agents, which takes a big step in the direction of general reinforcement learning agents. And joining me today is one of the co-authors of that paper, Max Jaderberg. Now, Max came to the Google ecosystem in 2014 when they acquired his computer vision company, and more recently, he started DeepMind's open-ended learning team, which is focused on pushing machine learning further into the territory of the sort of cross-task generalization ability. Max joined me to talk about open-ended learning, the path ahead for generalization, and the future of AI on this episode of the Towards Data Science podcast. I do want to get to the nuts and bolts of that paper and talk to you about it, but I'd also like to start with a more biographical question. How did you get into the DeepMind open-ended learning team? And then also just what is open-ended learning and all that? If you can squeeze that into an answer, that'd be great.
So my background is actually computer vision. So I did my PhD in computer vision. But since joining DeepMind about sort of 7 years ago, was doing some computer vision, thinking about unsupervised learning. How could that help reinforcement learning agents build agents that are sort of able to learn from interaction with their environment, and started exploring this space of, simulated worlds and games as a way to develop reinforcement learning algorithms. And this sort of led to quite naturally to these multiplayer games. Things like, we're familiar with things like chess and Go, but then actual multiplayer video games, things like StarCraft and Capture the Flag, Quake 3. These are great ways to build complex, interesting game environments that we can then try and develop our reinforcement learning algorithms, our AI towards. And when you're thinking about, okay, how do you create more and more complexity on the environment and then try and get an agent, an AI, to learn about that complexity, you then naturally want to make things even more complex and get it to learn even more. And you have this sort of ratchet effect. We do this naturally in sort of academia. We solve one problem, we solve Atari, and then we're like, okay, we need Quake 3. And we solve Quake 3, we're like, okay, we need StarCraft, right? But this sort of leads to the question, okay, actually, what if we could just forget about a fixed objective, forget about a fixed, one game that we have to solve or one objective that we have to maximize. And instead, we just define sort of a dynamical system, a learning system that continually grows in complexity. The agent gets better, but also the environment itself gets more and more complex. And as the agent grows in complexity, there's more and more in the environment to explore and discover. And so you just get, there's no end goal. There's just emergent complexity happening. It's a bit like artificial life. Anyway, that was a long way to say that through this exploration of these other games, I started the open-ended learning team in DeepMind. And this paper has really been our first concrete step in this direction.
Yeah, what I found really interesting about it was, to me, it seemed that this idea of environments being procedurally generated is like a paradigm shift in a way, because the focus, in my mind at least, the focus was always on we need to make better algorithms. We need to focus on the algorithm, come up with new, cleverer things. Attention was a step in that direction, and like self-play, that sort of thing. But it never occurred to me to look at the environments as the thing that deserved independent study. Was this a realization that was always obvious to the team at DeepMind, your team, to you, or is this something that just came about more recently?
Yeah, I think it came about a couple of years ago. Really, we had this process in, reinforcement learning research of you solve an environment, you create a new harder environment, and you solve that. But really, as I was doing a lot of this research, and a lot of my colleagues and people in the field were doing this, you would naturally realize that depending on what environment you have in front of you depends really on what sort of algorithm you need, and also like what sort of behavior comes out of these agents. And so it then started to make perfect sense that we actually need to start, if what we care about is an AGI, or on that route maybe a generally capable agent within some simulated domain, it makes complete sense that the actual like substrate, the environment that you're going to be training on, that you're going to be testing on, needs as much research focus as the algorithms that are going to be training on that and producing the final agent. So yeah, there's been a lot of work in, there have been procedure generated reinforcement learning environments before, like procedure generated mazes, and things like that. And there's been a lot of work from like the AI for video games community of like procedure generating levels for Mario or Zelda, or 2D games and things like that. But yeah, sort of putting it all together into sort of like one big reinforcement learning loop as well.
Yeah, and maybe this gets us into the paper more then, because this does raise the question, like, we have procedural generation at the level of individual games. What's the big difference between that and the kind of procedural generation that happens through XLand, the tool you use in the paper? What is it that those kind of procedurally generated levels of games don't do that now is unlocked by this new work?
Yeah, I mean, if you think about, let's say you think about a maze game, right, where every time the player gets plonked down in a new maze and has to solve this maze, you can procedurally generate the maze, right? Exactly what sequence of left turns and right turns you're going to have to make to solve the maze. But if you think about what's the underlying behavior that the player has to execute, even though the maze is procedurally generated and there's more mazes than atoms in the universe, right, that could be generated, the actual like behavioral side of the agent, or the player, the human player, is always the same, right, for each of these. Like there's a meta process of solving the maze where you hit a wall and you go left or right. So the actual number of behaviors is really small, even though the number of mazes is really large. So this led us to like, how can we procedurally generate not just the worlds, but also the actual games, the tasks that the agents have to play, so that we have not just one or two required behaviors of the agents, but thousands or even millions, ideally, required behaviors of the agent, which the agent needs to learn. So that's maybe the difference in the space that we tried, the design point that we tried to hit was, how can we procedurally generate worlds and games so that they require thousands and thousands of different behaviors, ideally, from our agent.
To like never give the agent basically the chance to overfit to a particular environment in any way.
Exactly. It's the deep learning thesis. If you have enough data, if you're asking like huge amounts from your network, then you will get generalization out of these neural networks. We've seen this in computer vision, we've seen this in language, and there's no reason that we shouldn't see this in reinforcement learning. We just need to ask, enough behavior out of these networks.
Yeah, to me, this is one of the fascinating things about this is oddly the parallel with large language models, in the sense that we have here finally it seems a task that's sufficiently hard that it forces the agent to generalize in that way, even though they don't seem related. I mean, it's kind of like the RL analog of that natural language task. Like, would you agree with that? I see you nodding there, so maybe that's approximately right.
Yeah, that's absolutely right. And this whole line of research came about from seeing the emergent success of these vision models and these language models, and there's no reason why this can't, like, the data modality is just slightly different. But yeah, it's absolutely that. It's keeping the neural network in this state of constant uncertainty where it can't memorize everything.
Yeah.
And so you have to learn general representations, general behaviors that work just well enough across this massive distribution of games and tasks that are being asked.
Yeah, it's interesting. There's a sense in which this seems like it's all about, well, obviously it's about making machine learning live up to its potential. But when you talk about deep learning, there's this notion of, deep learning model as a universal function approximator, and that sounds super promising at first. You kind of go, okay, so it can do everything, right? And then of course it turns out, well, at least until very recently, it didn't seem that way. But there have been a series of priors that we've kind of figured out what are the priors that we need to pack into these models. Which ones can we ditch? So we no longer, for example, hard code the idea that like an image has to be translationally invariant. We got, convolutional nets are no longer the only way to do things. Attention, though, was interesting because it gave us a prior that was, in a way, more universal, that seemed to apply to a wider range of tasks, but that was still very informative. Do you see something similar happening with reinforcement learning? Is there an analog for that progression in RL? Is it just the model that the RL agent itself has?
Progression in terms of the network architectures.
Yeah, exactly.
Yeah, I think we will see a similar progression in RL. I think RL hasn't quite had the same level of progression in terms of neural network architectures because there hasn't been the complexity of data needed to
Mm.
be soaked up by these new architectures, right? We can like even the networks presented in this paper are very small in comparison to these large language models and vision models. Um, but what we will see and what we are already seeing is that as the data becomes more complex, more vast, there's thousands and thousands of games that you have to learn and encapsulate within a network, thousands of behaviors do you have to express through one network. Then we'll see the benefit of scaling these models. We'll see the benefits of different architectures coming about. And yes, there are fundamental operations, think like attention, or this there's a generalized class of just multiplicative interactions between parts of your data that seem to be work really well across all different types of data: vision, language, RL, speech.
And on the qualitative side, like what do you see from these agents that you don't see from, let's say, a StarCraft playing agent or something like that?
One thing in particular that I think surprised us was this experimenting behavior that we saw coming out of these agents. So they're very, very robust to uncertainty because they've been trained on so much vastness. They come into a new game, a new task, and they often don't know what to do. They don't know how to solve it. It might be obvious for you and me if we were told the rules, but they don't know. But it might not be obvious for them, for the agent. And we see this experimenting behavior come about quite often, where the agent doesn't know exactly how to solve the task, but it might know some of the objects involved, and
Mm.
it will just sort of juggle these objects about, or try different combinations of arrangements, or um, search for different things and put them together. And then sometimes through this experimentation, it happens to get the right arrangement of stuff where it puts the right thing in the right place, and it recognizes that, and it can recognize when it's successful. It's like, oh, I needed to get that next to that and that next to that, and I didn't know how to do it, but now I can see it and it's right. I'm going to stop juggling things, right? So this amazing behavior came out of experimentation with success recognition, which is sort of a general behavioral heuristic. At the moment, the sort of behavior we're seeing is it very quickly narrows down the types of things it's experimenting with,
Ah, okay.
but doesn't necessarily refine things as it's going. So
Interesting.
it's not doing this sort of online adaptation, which we really wanted to see want to see at some point.
One of the things you tested in the paper was cooperation and competition. So, introducing other agents to the environment, having a combination of individual games and group games. Did you see a difference in terms of performance? Because I imagine managing an environment with another agent is more complex. Like, were there these similar kind of emergent behaviors trying to feel out the cooperation dynamic, maybe trust building or things like that?
Yeah. So the really interesting thing is that we actually it's a multiplayer game, right? A multi-agent environment. So there's many agents in there. The way we trained is actually we only per game there's only one agent which is learning, and the other players of the game are these frozen players. They're pre-trained agents which have some behavior, and there's like a catalog of maybe 10 or 12 that we created, and that's what we train against. But they don't change. So from the training perspective, this new agent, as it's training, has to learn to play with all these different types of agents that come at it, and um, yeah, sort of maybe change their behavior based on who they're playing against. The interesting thing is, after the fact, we can then measure the cooperativeness of the trained agent, how cooperative it is, how competitive it is, with like these probe tasks where we construct little game theory dilemmas, like prisoners dilemmas and things like this, and we can see how the cooperativeness of the agent changes through training, and this is purely based on its experience in the game world.
And what is maybe this is an impossible to answer question, but what is easier to learn? Is it the cooperative dynamics, or does it tend to be the competitive dynamics?
I think the competitive dynamics are the easiest thing to learn, and or maybe put another way, competitive games are a very strong source of training signal. You
Mm,
have this very natural like auto curriculum effect, where as the opponent gets stronger, the game gets harder. So and if you're playing against yourself, as you get better, the opponent gets better,
right.
and so you naturally get this sort of easy, gradual learning like curriculum to play with. Um, if you think about learning cooperation, it's actually very hard because you need to have another competent agent in the environment
Right.
and then watch what it's doing and learn that it's competent, and actually like learn some behavior which complements that other agent's behavior. That's a lot of steps. And competitive behavior, you don't even need to think about the other agent. You can just think, oh, look, whatever this agent does, it's going to be against what I do. So do something to like get rid of it, or you know leave it aside.
I guess competition is like the essence of self play as well, right? I mean, it's basically a tried and true method.
Exactly. The cool thing is like mixing all of these games up together in one big soup during training. um, Both of these things can emerge, and you know early competitiveness can lead to later cooperativeness um, through this training dynamic.
And what do you see as the kind of the big bottlenecks right now? Like, what prevents these agents from doing more? What are the kinds of mistakes they'll tend to make, and what do you see as the next steps in terms of iterating on this?
So as I was sort of saying before, we're seeing great what we call zero shot behavior, so that you know a new task is presented to the agent. Maybe you come along and you create a little task and you give it to the agent, and it does something kind of sensible. It's generally capable. It solves it some of the time through experimenting or by kind of knowing what to do. But what we don't see is, as the agent keeps playing on that task over the course of minutes, that it gets better at that task. Like
Mm.
me or you would sit down on this task, and initially we might not know exactly how to do it, but we'd stumble about and manage to do the task. And then as we played for another 5 minutes, we'd get better at this task, right? We're not seeing that from the agents now. And it's this sort of online adaptation over the course of minutes that we really want to see, and which is sort of the next stage of this project to try and get that out. It's a bit like with the GPT-1 moment where you know things are working and like cool text is being emitted, but we don't yet have this meta sort of behavior where you can um, the agent will understand what's being asked of it right now and change its behavior for the next few minutes based on that.
And do you think, like the GPT series, do you think the answer here is scale?
Yeah, I mean, it's scale, but the trickier part in reinforcement learning is, like we were talking about before, the environment. We don't have the data readily available. We can't just scrape the internet for um, you know millions of hours of Xland gameplay.
Right.
Um, we have to somehow create a dynamical system, a reinforcement learning process that generates that experience, which is rich and interesting, to feed these big models and get adaptation out. So it's scale, and also how we actually find interesting tasks, generate interesting tasks, and get agents to train on these.
And like measurement of generalization is its own interesting sub area here. Like, how do you know that you're making progress in training these agents and scaling and doing whatever you're doing here? Notoriously in language, this is tough because we've got a whole bunch of different metrics. We've got like the blue score. There are a whole bunch of different ways that you can assess through Q&A, through translation. So how do you think about measuring generalization in the context of an environment that's so diverse?
Yeah, it's a really good question. You know, you could think of like any other data set. You just measure. You have a training set, and then you have a test set which is held out, right? And you train the agent on the training set or some training distribution, and then you run it on the test set, and you look at the scores. And then you could say, oh, look, what's the mean score, the average score, or the median score? And this might tell you something, but about how it generalizes to these held out test levels. But it might not tell you about like this distribution. If the distribution is very vast and diverse, then we might not care necessarily about the mean or the median.
Mm.
What we might care is that, um, you know, does your agent do, superhuman on a few levels and then catastrophically fails
Right.
on like the 90% of them, right? Or do we care more that our agent is sort of, you know, 30% human level across 99.9% of levels, right? So catastrophically fails in as few as possible. So we kind of care about a blend of this stuff. It's not obvious which one we care about more, which one we care about less. So instead we look at what we call percentiles. So rather than just the median, which is the 50th percentile score on a test set of levels, you can look at, okay, what's the sort of 10th percentile score, all the different scores and what that distribution looks like. And we're trying to push all of them up at the same time. They're kind of in conflict with each other, which is
Right.
the interesting thing.
It's sort of, well, a Goodhart's law problem, right? I mean, ultimately, the moment that you define a single metric that you want to optimize against, you kind of overfit to it, and then it ceases to be a good target. These games also have different reward profiles, don't they? So some games give like a ton of reward, and then others have more limited reward. How do you make sure that an agent that does really well at a game that gives a ton of reward, but poorly at a game that gives little reward? How do you kind of balance that out?
Yeah, I mean, the reward scales for these games are completely different. And because they're procedurally generated, no human has looked at them. We can't say
Right.
whether like, is a score of 100 good, is a score of 10 good, like what would a person do on it? We can't possibly put enough people to set these like human scores on these levels. So um, instead we um, sort of iteratively feel out what's the best score on these levels by just taking, the best agent we have at the moment and normalizing by the score of that agent.
Mm.
And that just gives us like a rough estimate. Okay, like maybe a score of 100 is what our current agent can do. So we'll call that, the benchmark, and then see if we can push above that. And so we iteratively like renormalize um, by whatever agent is best as we train these generations of agents.
Interesting. Yeah, a lot of different self-growing ladders in this whole architecture.
That's one of the sort of signatures of an open-ended learning process, is that there's
Mm.
no sort of fixed number that you're just trying to push up, right? And there's a known top end of that number, right, or a known bottom end of that number that you're trying to push down. Instead, a signature of an open-ended learning process is we don't know where the end is, right?
Yeah.
And we're just going to like iteratively move there, and we can maybe measure that we're going in that direction.
Well, do you think, because I remember in the GPT-3 and scaling laws, actually the scaling laws paper that came out before GPT-3, there was talk about the place where the scaling laws were expected to break down, at least for the particular transformer model that OpenAI was working with. Do you have a sense of how open-ended this process is? Is there any reason to think that this does not eventually just lead to AGI as these environments are just made more complex with roughly the same model architecture?
I'd love to believe that, um, but I'm sure there are many flaws in the current algorithms, um, and for sure, I think a limiting factor at the moment will be the size of the networks, the model architectures
Mhm.
themselves. Um, and then you have the expressiveness of the environment as well on the other side. Like how much different behavior can be expressed in this environment. Um, so there'll be limitations from those two things at the moment. Um, but maybe on an algorithmic level, some flavor of these, you know, open-ended learning algorithms, for sure, I could see this as being a scalable way to move towards AGI.
And do you think that this is teaching us something? I'm always curious about this. So my background is in physics, and so in physics, you always think about sort of fundamental things that transcend, what we think of ourselves. And when I look at machine learning, there are a couple of areas that seem to flirt with this. So there's like attention that seems to be one of these things that's universal, or that seems to apply to a whole bunch of different domains. In reinforcement learning, we're seeing now kind of this ability to generalize and the tendency to learn experimentation behavior. Are there other things like that or first off, would you agree that those are kind of, it's somehow that they may be fundamental? Obviously, we can't know, but is there something about our universe that just like biases towards this behavior at a level that goes beyond just what we happen to do?
Yeah, it's a really deep question. And it's so tough to say. There's like there must be some sort of fundamental like physical processes, like the fact that entropy is always increasing,
Mm-hmm.
that leads to sort of natural competition of states between physical stuff, right? And so what we end up seeing through time are the things that survive the bombardment of like entropy from the universe. And you know, dot dot dot, we get things like actual evolution of intelligent creatures and you know the living world on this planet. Um,
This is like a very ill-formed thought at my end, but it feels as if there may even be a result that I'm not aware of here that actually speaks to this directly, but it feels as if environments almost imply a loss function in a way. Like the systems that persist stably in any environment must be optimized with respect to something. And that connection between environment and loss function seems like something fundamental that might speak to AGI, but again, this is like half baked and speculative.
yeah, no, I think that's true if you say I'm going to take a point in time, like right now as we're speaking, I'm going to freeze, right, and say what was the loss function that got the universe to the point now,
Right.
given some underlying dynamics, and there would be a loss function that if you optimized it with some optimizer would get you here. But as soon as we go an increment of time, that loss function would be different, and we froze there. That loss function would be different. Um, I'm not certain that there is a fixed loss function um, that, if you optimize, you would get to this open-ended emergent, you know, universe. And an AGI sort of simulated equivalent, I'm not convinced there's a single loss function, right? When we say single loss function, sort of like fixed data
Yeah.
that would get us there.
I guess if we knew it, we could build an AGI, or at least we could scale towards an AGI much more
Yeah,
easily.
I, maybe I'll eat my words and it's like, oh, it was obvious. It was just this. It was log loss on something. But no,
Yeah, right. It's always log loss at the end of the day.
it's always
Yeah.
log loss.
Looking at these agents, some of the behavior, and we're talking about things that generalize. Game theory, again, seems to be, I don't know, I might eat my words here, but game theory seems to be something that generalizes as well. I'm curious which of these agent behaviors kind of reflected, if you saw any that reflected an understanding of game theory in sort of surprising ways. You referred to the prisoner's dilemma, things like that. Were there ways that these agents seemed to display particularly clear consciousness of some of those principles?
I would say not clear consciousness,
Oh, yeah, bad word.
but I would sort of dissociate intent of the agent
Right.
from what we measured the agents doing, so to speak. And I think we did see in some scenarios that agents were um, sort of, you know, doing sensible stuff under the model of game theory. So game theory, you would give a situation to these agents, and then you would assume that they're completely rational and they know that they act completely rational, and you would see what they would do. These agents don't act completely rational, so they're sort of far from the game theoretic solutions. but maybe they do a little bit on the rational um, scale. Um, I would say this is just like an emergent property of the training system, and at least from like my observation, like I've watched thousands of these videos now, like through this project, and I can't really say there's much intent that they sort of know consciously that this is what I should be doing because of this game theory.
I should watch my anthropomorphizing of AI systems here. But one thing it does make me think of is the sort of, there's like, and again maybe this is wrong, but it feels like there might be an analogy between this let's say demonstrated compatibility with principles of game theory, and when you look at GPT-3, what it does with arithmetic. So a lot of people were talking about, GPT-3 fails at adding numbers that have more than X many digits. And this was taken as an indication that the model had not learned principles of logic. There was sort of this idea that, it fails at generalization because it can't learn the logic behind this. The common rebuttal there was like, well, have you ever seen humans try to add large numbers? It doesn't, like, it's sort of similar. This is kind of what it makes me think of here. You've got this, what seems to be a principle of logic, and maybe it would be a good bellwether in the same way. Would that make sense as a...
Yeah, and I think this is exactly right. Like, especially in AI, we're so used to trying to get like these perfect logical responses out of the problems that we give these systems. But if we look at like all the sort of developmental study and behavioral studies in the animal world, including on humans, right, we don't see logical responses.
Right.
We don't see rational responses. We see what we call heuristic behaviors which aren't optimal, they aren't rational, but they kind of generally work, and they're very, very low complexity to compute and execute. So like a great example of heuristic behavior is trying to catch a ball, right? You don't look at the ball and estimate its velocity and acceleration, the wind dynamics, and then run a differential equation solver in your head, work out the point where it lands on the ground, and then move optimally towards that point to catch the ball. You don't do that. Like, there's this well-known gaze heuristic where you look at the ball and you move iteratively to keep the angle of your gaze to the ball constant. And if you move like this, you'll end up intercepting the ball. Or even if it's not a ball, a frisbee, a glider, whatever it is, it's a very general solution to, catching something, which is very, very low complexity. It's not optimal at all.
And does this make you think about symbolic learning differently? I mean, like, there's obviously the argument that, or the debate as to whether this feature that you just described is a feature or a bug. And you can choose to look at it either way as like, well, this is imperfect logic, so these systems are hampered by their inability to do this kind of fundamental reasoning. Or you could look at it as like, well, systems that reason this way are able to build AI systems today. I mean, that's what humans do, and therefore we should just invest more in that direction. Does this kind of inform your intuition as to whether symbolic logic might be promising?
Yeah, I mean, I very much see it as a feature to get these heuristic behaviors out. And, symbolic logic is fantastic when, the model is correct, right? When the formula is correct and the symbols are well defined, right? It'll extrapolate, it'll generalize perfectly, right? But when it's wrong, it'll catastrophically fail, right? Because there's no flexibility with the symbols, right? On the other hand, you have these like heuristic solutions which are built up from just like statistical, averaging and these statistical methods. They don't extrapolate. Sometimes, on the face of it, they don't extrapolate really, really far, but they could have a very wide support. And crucially, they might be very robust and not fail if things are slightly different to how they were formed.
The physicist in me wants to go to Feynman here, but there's this quote where Richard Feynman says, like, I think it's safe to say that nobody understands quantum mechanics. And the implication is that, there's something counterintuitive about quantum mechanics, but the implication is also that we understand other stuff in a different way. So for example, like, we tell ourselves the story that we understand what a ball is, and we kind of apply a sort of symbolic logic like filter or to the story that we tell ourselves about it. It's as if there's like this entity called a ball, and then we know everything about the ball, blah, blah, rather than what you just described, which is just like, as babies, we rolled balls around a lot. We developed a series of heuristics, and those heuristics added up to the illusion, the impression that we understand it. And through that lens, you could say that we absolutely could understand quantum mechanics. This is the heuristic process does generalize to kind of completely alien lands if we do apply it consistently.
And the key thing is like, what came first, like the word of a ball or the understanding of how a ball works,
Hmm.
like through symbols and language and mechanics, or knowing how to roll a ball, or that a ball will roll down the hill to you, right? The knowledge of how a ball just like behaves in the environment and how you should act to like pick up that ball and roll that ball comes far, far before in human history than understanding that the ball is an object and like these are the forces and laws of the ball, and like um it's the same thing with almost all human inventions is like the invention comes far before the actual like understanding of mechanically how
Right.
it works, or how you even verbalize you know why it works.
That's interesting in and of itself for its implications for, I guess, AGI and generalized learning. Obviously, we're the one shining example of like the triumph of generalization ability in the universe. But we ourselves are the product of, as far as I can tell, at least two different learning processes. We have evolution that gets us, to the moment that we're born, and from there, a separate process of optimization happens where our neocortex gets formed and starts to couple with our limbic system in interesting ways. I mean, I guess this could be framed as a pessimistic argument for any kind of consistent strategy for training, because you could argue, well, like we know the one example of a generalized learning agent or a generally capable agent that we have comes from two distinct learning processes. So the hope is we can get a generalized agent from just one, which is technically unproven, or there isn't.
It depends what you view as learning processes, right?
Mm,
So I often use the analogy of training the weights of a neural network with stochastic gradient descent. You're actually training the neural network. That's the process of evolution. And then when you run the neural network, that's the process of birth and starting to build up the representations. When you have recurrent neural networks, where as you step through the environment and experience time, the internal state of the network gets updated. Things like transformers, LSTMs, these are all recurrent neural networks.
mm.
Right? Transformers are maybe a bad example because they are not perfectly recurrent, like infinitely recurrent. Um, you can think of these activations being built up through time as a learning process, and there are even recurrent neural networks which model sort of brain learning and have Hebbian dynamics, right? So in that sense, we have two learning processes. We have evolution, which is training the weights, and then we have running the network in the game with a recurrent neural network, which builds up the internal, you know, activations, which can be thought of as weights as you experience more.
Interesting.
Um, yeah.
That makes so much more sense than the way I was thinking about it, which was like, you're born, and that's equivalent to having a blank slate architecture. Of course, we know it's not actually a blank slate. So to your point, you need those weights to actually be trained ahead of time. So, do you have a sense then of what the next class of environments, the next challenge is going to be? We talked about scaling and that being the goal, but do you just make the environment more expressive in a certain direction? Do you have a hunch about what direction that might be?
Yeah, it's really tricky because we can't just make a world simulator.
Right.
Like there's too much complexity. Like no amount of game developers is going to be able to do that. So we have to sort of intuitively nudge out the complexity and features of our environment in ways that we think are going to add huge amounts of like combinatoric complexity. So we often think about like adding new ideas onto this environment where we add a new feature which interacts with all the existing stuff in really interesting, chaotic, non-linear ways that you can't predict. These are the sort of features we're looking for. Um, and crucially at the moment we're thinking, okay, and how does this lead to situations where adaptation of the agent's behavior over the course of a few minutes would really lead to like nice payoffs for the agent.
Right.
um, so we can try and encourage it emergently to learn sort of adaptive behavior.
Do these results that you've seen, as impressive as they are, do they make you think of alignment differently? Do they overlap with your sense of what's important for AI safety, for these things to be deployed responsibly and so on?
Yeah, we have a great AI safety team here in DeepMind, and there's I think one of the dominant things for me is it's very difficult to a priori know what the emergent behavior is going to look like and what's the coupling of environment and training algorithm and model architecture is going to produce behaviorally.
Mm.
So I think it's going to be exceptionally important to bake in, like, as we're training agents within the training loop, bake in these sort of alignment mechanisms, safety mechanisms, right, that are always acting rather than just waiting till the end of training and something
Right.
pops out and then check, oh, is this aligned or is this safe? No, like we can't, like there'll be a future where that's too dangerous. We can't do that. We need to like have this alignment, these alignment mechanisms, these safety mechanisms as part of the training loop,
Mm.
because we don't know where this like training system is going to go.
And I guess related to that too, it kind of feels like there'd be an interesting opportunity to do a little bit of forecasting research potentially, in the sense that, like, one of the things that surprised everybody about, again, things like GPT-3 and scaled models was the emergence of all these capabilities that nobody predicted or nobody knew when they would come. I wonder if there's an opportunity here to do something where, you say, okay, well, let's investigate the effect of adding a particular kind of perturbation and see what capabilities arise from that.
Yeah, definitely. I think there'll be, you could do really interesting studies like this where you change some of the environmental factors, you change some of the learning factors, and you see how that like emergent behavior, and how that alignment changes. Um, like some colleagues here, Joel Lebo, um, they actually like construct, for example, these environments which are set up to be social dilemmas, right? Things like, oh, there's a collection of agents and they have to, um, there's apples, but if they eat all of the apples, then the apples won't grow back. So they have to
Mm.
collectively, um, work out to not eat them all and have a little contract between themselves. Many, many examples like that. And what you can do these amazing studies where you change the density of apples, like how connected the like islands are, like how well people can see each other. Can they even recognize individual different agents, or all agents are sort of look the same to them? And you can see how like changing these factors results in different emergent behaviors, different types of cooperation and alignment. And you can do the same experiments on human participants as well,
Wow.
and sort of map those responses.
That would be, I mean, there's something that seems to speak to a lot of deep questions there, almost philosophically, like free will and agency, to the extent that these agents just seem to, or the we just seem to replicate the behavior of agents with very simple priors. It sort of makes you wonder. One last thing I do want to ask you about is how's this impacted your view on timelines towards something like AGI? Like, does it feel closer to you now that you've seen a result like this, or is this more or less consistent with your priors from before?
I think definitely, as more of these sort of results come out, the sort of confidence
Yeah.
that this is possible just increases, more and more. And definitely for me, this result is again just more. There's more confidence that this is possible. Um, on timelines, it's just so tricky to forecast. But yeah, I am like quite optimistic about our current set of like algorithms, neural networks, scaling these things, to at least like move us incrementally towards this AGI target that we have.
So prosaic AI feels like it's feeling like a pretty good bet that some combination of RL, self-play, neural nets is gonna do it.
Yeah, I mean, like on the exact methods, it's hard. Like, um, I can't see, theoretically, it's hard to see why not like neural networks with the right architectural biases and things
Right.
couldn't like really get very close. Um, but yeah, maybe we're missing something really fundamental, and that's completely possible. I'm probably just too optimistic about this. Yeah,
Well, that's the great mystery of intelligence, right? I mean, if it was obvious, then well, it would have been done. This is
exactly.
Thanks so much for sharing all this. A really exciting topic and a fascinating time for open-ended learning. Do you have a personal blog actually that you'd like to share anywhere where you collect your thoughts that people could check out?
No, probably the best place is my Twitter, at Max Jaderberg.
Perfect. Okay, we'll be sure to include a link to that as well in the blog post that'll come with the podcast. So thanks so much, Max. Really appreciate it.
Brilliant. Thanks a lot.